Hello everyone, I hope you all are doing well. So now we will be starting with the chapter Limit, Continuity and Derivability. So basically this is the start of our chapter of differentiation basically. So before we directly get into differentiation, there are a few things that we need to understand, which is about limits, continuity, their geometrical representation, etc. etc. So we will be looking into those things in this chapter. Later on, there is another chapter based on the concepts of this chapter, which is application of derivatives, which we will be doing straight after this chapter. There you will see that the use of differentiation is a lot compared to this chapter. So let's start. So first of all, in this chapter, the major portion that we are going to cover is limits. We are going to see basically what limits are, how they define graphs, their properties, and how we can solve them. We are also going to look into a few expansion series, which is known as our Maclaurin series. Then we will be looking into our continuity, properties of continuity, and then we will look into our derivability. Again, continuity and derivability will be not into much of our focus in this chapter. We will be focusing more on limits. So let's start. First, let's look at what basically a limit is. The limit of any function f of x at any point x is equals to a represents the value of f of x that it approaches as x gets closer to a. That means we are not considering here that x is equal to a. We are saying that x is approaching a. That means x is a value which is very close to a. It is either going to be, let's say, a plus a very small value or a minus a very small value. So that is what we are saying. So here, let's say if we find out that this is our function and we put limit x tending to a, if we try to find this value out and if it comes out to be L, which is nothing but a finite value, if we get a finite value out of this, that means we can say that our limit exists at that point. And what is the value of that limit which is existing? Its value is L. So first of all, again, before I get deep into this, a few basic things that I want to tell you. Let's say I have this value a. This is my number line. I have this value a. Now, what do I mean by I'm approaching a? I'm not, my x value is not equal to a, but it is approaching a. That means either it is going to approach a from the right hand side or it is going to approach a from the left hand side. Now, if I talk about the right hand side, what would be just this value here? This is going to be a point zero 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 something. So this value, what do I call this? I call this as a plus. And this value, when I'm approaching my a from the left hand side, that means my, what would my value be just close to a? It is going to be a minus 1.99999 something. So what do I call that value as? I call it to be a minus. Let me take an example for you. Let's say if I have a is equals to 1. Let's say my a is 1. So what do I mean by a plus? A plus, which is going to be 1 plus. So 1 plus would be 1.00000001. And when I talk about a minus, which is going to be 1 minus, I'm telling the value would be 0.999999, and it goes on continuously. So that is what I'm telling about a minus and a plus. That means one thing that you can make sure about a plus and a minus is that a plus is going to be greater than a and a is going to be greater than a minus. So this is one information that you must keep in mind. Now, whenever I talk about limits, I generally find out my limits using both these values, my left hand limit and my right hand limit. If my limit comes out to be the same from the left hand limit as well as from the right hand limit, then I say that my limit is existing at that point. And if that value comes out to be finite, then my limit is existing basically. If let's say my value would come out to be infinite or some type of indeterminate form or undefined, then I cannot say that my limit is existing at that point. So keep this thing in mind. Now, if I was to tell you with the help of a, let's say, any example of a graph, let's say this is my graph. This is basically a logarithmic graph. Let's say at x is equals to a, the value that I get for y is going to be f of x. Let me consider this. So what do I mean by approaching the value a? That means I'm approaching a from here and I'm approaching a from here. That means my value at this point and at this point should be approximately equal to f of x. That means the value would be so close to f of x that I can directly write it down as f of x. That is what I'm trying to tell you from the limit perspective. So keep this thing in mind. Now again, explaining how you can solve your limits. Any function would be given to you. You would be asked to find out whether the limit is existing at that point or not. So first you would find out your left hand limit, then you would find out your right hand limit. If these two comes out to be same and are equal to a finite value, so this L is basically a finite value. If this is true, then what I can say is that limit exists at point x is equals to a. Then I can say that my limit is existing at point x is equals to a. Now, in my function f of x, I'm not putting x as a. I'm putting the values which are very close to a. Now, let me tell you one more thing about this. Let's say if I have a plus. What do I mean by this is I'm talking about a plus h. Here, h, and when I talk about a minus, it is a minus h basically. Here, h is a very small number, very small number, close to zero, close to zero. So I can, if let's say it is problematic for me to solve my function in this manner where I have a plus and a minus, then I can write it down in this format also. X as a plus h, sorry, a plus as a plus h and a minus as a minus h. Here I'm considering that h is a very small value. It is going to be 0.000000, and after infinite zeros we are going to have a 1 there. So keep this thing in mind. Now, let me tell you how basically you can solve different types of limits. Let's say you have limit x tending to a plus f of x. So what are you going to write down? How can you write this down? Basically, this can also be written in this format. Limit h tending to 0. Here again, I hope you all remember. Here I was saying that h is a very small number. It is close to 0. That means I can say that h is tending to 0 and I can write this down as f of a plus h. So this is how you can represent it. Now let's say if I had limit x tending to a minus f of x and I needed to find out the value of this, I can simply find out limit h tending to 0 f of a minus h. Now this is generally for us to understand and solve complex problems where let's say we have modulus, greatest integer function and all those functions. That time we can use this format. Apart from that, you can solve questions of limits using our approximations methods and a few more other tricks. Now, one thing, let me again show you with the help of a graph. Let's say this is my graph. This is my a value here. This is the value that I'm getting at f of x. Now, let's say if f of a plus h, which is going to be very close to a. Now, at this value, if I get it close to f of x, now, of course, this value is also going to be very close to f of a, right? This value was, sorry, f of a. And here I'm going to have f of a plus h. And here, very close to a, I'm going to have a minus h as well. And this value should also be very close to f of a, which is f of a minus h. Now let's say if this comes out to be different, f of a plus h is coming out to be something else, f of a is something else, f of a minus h is something else, then we can say that a limit is not existing at that point. If my limit is not existing at that point, that means my graph basically is discontinuous at that point. That means it is not going to be a smooth curve. It is going to be distorted. It is going to be up till here, then here, then here. So it is going to be in a point format. So understand this thing about limits. Let's look at this question. Now you can see that we have been given limit x tending to 5, x minus 5 modulus upon x minus 5. Now, one thing that you must remember in limits is that whenever you have a 0 coming out to be in your denominator, you have to remove it somehow. You can have a 0 in the numerator, but not a 0 in the denominator because it is going to make it undefined, right? Now, if you look at this function, basically, if I consider this function to be f of x, let's say my f of x is equals to x minus 5 upon x minus 5. So what would my value of x of 5 be? When I take x is equals to 5, exact value, I would have a 0 on top, I would have a 0 below. Now you can see that this value is basically undefined. I cannot find out the value of this, right? 0 by 0, we do not know what is it going to be. So we call this as the indeterminate form. So this is basically in the indeterminate format. So there can be various ways in which your function can come out to be indeterminate. We'll look into that in our next slides. How or what are the different types of indeterminate forms of any function that you can get. Here we are getting it to be 0 by 0. That means we cannot put the value of x as 5. Now we need to find out our limit. So what are we going to do? First, let us define our modulus function. How do we define our modulus function? This is my modulus function. So what would its value be equal to? Its value would be x minus 5 only when x is greater than 5. When it would become 0 when x is equal to 5. And when x is less than 5, what would it become? Basically minus of x minus 5. This is how modulus sign is opened, right? I hope you all remember this theory we had studied in functions chapter, how we can open up modulus. It opens up negative when the value inside or the function inside comes out to be negative on a certain value. So for x less than 5, it is going to be negative. That is why I'm writing it as minus of x minus 5. Now what I'll do is, now I'll try to find out my limits. Now for limits, what happens is, I'll simply first of all find out my 5 plus value, which is my right hand limit. And then I'm going to find out my left hand limit, which is nothing but my 5 minus value. So 5 plus is basically 5 plus h. That means it is going to be a value greater than 5. So what would my f of x become for this case? It would simply be x minus 5 upon x minus 5. Here this 2 would cancel out as 1 and I would get 1 as the answer. So this is the value of my right hand limit. Now if I talk about my left hand limit, I have basically 5 minus h here. That means I am having a value which is a little less than 5. It is not 5, a little less than 5. And we know whenever we have a value less than 5, how does our function open up as minus of x minus 5? So my f of x would basically become minus of x minus 5 upon x minus 5. Here this 2 would also cancel out and this would come out to be minus 1. So here you can see that I have found out my LHL and my RHL. Now you can see that these two values are finite, right? These two values are finite, but they are not equal. My values are coming out to be finite, however, they are not equal. That means at 5 for this specific function, my limit does not exist. And what was the condition that we studied for limit? I hope you'll remember my left hand limit should be equal to my right hand limit, should be equal to a finite value L. However, here I'm getting those values to be finite, but they are not equal. That means my limit does not exist at 5. So what would be my answer? Limit does not exist at x tending to 5. Had this been some other value, again, we would have checked it for some other value. At 5, it is not existing. So I hope you must have understood this question properly. Now there are a few properties of limits which you need to remember. Again, what is our sum rule? Sum rule, let's say if you have two different functions, you can separate it out into different limit functions. Product, you can also do two different products for two different functions. Quotient, it also revolves around the same practice, provided in our quotient rule, whatever function is below in the denominator, provided that limit extending to a gx should not be equal to 0. Of course, if I get a 0 in the denominator, it would become undefined because the value is not known to us, right? That is why this condition is provided. Constant multiplication, constant can simply be taken outside. So keep this thing in mind. Now there are a few common indeterminate forms that you need to remember. First one being 0 by 0, as we looked in our question. Sometimes you can get infinity by infinity as well. Sometimes you can get infinity minus infinity. Sometimes you can get 0 into infinity, 1 to the power infinity, 0 to the power 0, infinity to the power 0. Of course, these are indeterminate forms because you do not know what their value is going to be. Let's say if I have an infinity in my denominator, my value would become 0. However, if I have an infinity in the numerator as well as the denominator, I do not know what that might be, right? So that is why it comes under an indeterminate form. And one more thing that you must remember is that infinity plus infinity would give you infinity. Now, this is just for you to understand because infinity is a very big value. Again, infinity is a very big value. If I add them up, it is not going to be 2 times infinity. It is going to be, again, infinity only, very big value. So keep this thing in mind as well.